Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about optimization of filter banks. So let's get started. Our goal is to obtain a filter bank from our structure or our product. It's the folding matrix times the delay matrix and so on, which has good subband filters. For example, good or sufficient stop band attenuation and not much passband attenuation. An example could be a desired stop band attenuation of -6 dB and a passband attenuation of less than -3 dB. So what's the problem to solve? The coefficients which determine the frequency response are the coefficients in our cascade or our product and are the coefficients in our matrices. They result in the frequency response in a nonlinear way, hence the usual filter design approach, they don't work here. So previous approach like the Remez exchange algorithm, for example. So those traditional filter design methods or algorithms can also be seen as an optimization algorithms for more or less linear problems, or maybe quadratic if we take the mean squared error. We know that we can read out the resulting analysis baseband prototype impulse response HA of n, for instance, by computing the sparse folding matrix of the product given here, without the transform matrix T. And then if we compare it to equation 1 from lesson 14, it was this matrix shown here with this diamond shape. And then in this way we can obtain a HA of n and hence its frequency response from our matrix coefficients. So we can do the same for the synthesis side, or if we restrict that our matrices to have the determinant equals to -1, and then in this case the synthesis baseband impulse response is the same as for the analysis. Another possibility to obtain the analysis baseband impulse response is to compute the polyphase matrix PA of Z, and the first column contains the polyphase elements of the first subband filter in reverse order, and this can be used to read out its impulse response H0 of n, and then to obtain the HA of n we simply divide H0 of n by the modulation function for the first subband for k equals to 0.